So hi guys, we are back with another video. That is, we are going to discuss the past paper questions from 1994 onwards, maybe up to 2020, right? So that is only related with the Newton's laws of motion problems, right? So Newton's laws of motion and force and momentum change, not the conservation of momentum part though. Simply it's force and momentum change and also Newton's laws of motion, right? So based on that section, we are going to analyze all the MCQ problems from 1994 to 2020 as much as possible as a video series, right? Okay guys, let us get on with the question given based on in 1994, the question on 1994, right? So it says an object of mass 5 kilograms is subjected to a resultant force capital F, right? So there is an object of mass 5 kilograms, right? An object of mass 5 kilograms. This is subjected to a force of capital F, right? Which varies with time as shown in the graph, right? So according to FT graph, they have shown how the force varies. Initially in the first 2 seconds, the force has uniformly increased, and in the next 4 seconds, next 6 seconds, it was uniform, and then it has decreased, right? So what they're asking is the momentum gained, right? Momentum gained within these 10 seconds. Okay, simply, if we see guys, now if we apply F is equal to mv minus mu over t, right? And if you multiply f and t, f into t is equal to what? Delta mv, change in momentum, or else the momentum gained. Change in momentum, mv minus mu gives us what? The momentum change, the linear momentum change. Now f into t is what? Force into t. How to find f into t? This f into t can be given by the f into t. F into t, right? F into t can be given by the area under this curve, guys, right? Area under this curve. If you take the area under this curve, obviously it gives us the f into t part. So what? So this is actually a trapezium. It's a trapezium, right? So how do we find the area for trapezium? Half into perpendicular height is 5, and and then we'll have to add the summation of the parallel sides. The parallel sides, 2 to 8 is 6, and this is 10, right? So the area is going to be half into 5 into 16. This cancels out 8, so it's going to be 40, right? So f into t product is 40, therefore delta mv is 40. How do we write a momentum change? 40 newtons second, right? 40 newtons second. That is the third answer, right? The third answer, right? Right. So if we see the next problem, this is a question from 1995, right? So yeah, let us see this question. So actually guys, they have given the velocity time curve of a particle of velocity time curve, right? Velocity time curve of a particle of mass m moving along a straight line in the shown figure. Actually guys, so these kind of problems are very frequent, right? So that is, they will usually give you 3 statements, and then you will have to check the validity of those 3 statements, like, so whether A is correct, whether only B is correct, whether ABC is correct, like according to the solution given below, right? So you need to check one by one in this case, right? You can't straight away like, okay, if this is correct, you can't go and say only A is correct. You'll have to check B and C as well, right? So therefore, like when you are given with ABC statements, you will have to be very careful, right? So okay, let us see what the statement A says. It's simply the particle returns to the motion. Returns to the motion. Returns back to the initial position, I guess, right? So I guess this is a pretty mistake or something. Anyways, it doesn't matter. Let us assume it started from a point A. Well, let's assume it started from a point A. All right. And then it moved. Okay. So what does a velocity, the area of velocity time curve gives? The area of velocity time curve gives the displacement, right? So V into T gives the displacement. We have learned these things under graph lesson. So this has a positive displacement, isn't it? This has a positive displacement. Since this has a positive displacement, we assume it's moving positively, maybe a positive s distance. A positive s distance. Let's assume this point is point B. Now what can you say about this curve? This has a negative area, right? Half into base into perpendicular height. This has a negative area. Negative area denotes what? A negative displacement. And if you see, both this area and this area are the same, isn't it? Both this area and this area are the same. Base is T, T. Height is V, V. So therefore, it has a negative area, which means it has a negative displacement of S. Negative displacement of S means it is returning back to its original position. Negative displacement means, because like you know, displacement is a vector quantity. So therefore, the negative implies the displacement is in the opposite direction to that we considered. We considered this direction as the positive direction. So negative displacement means that the displacement is increasing in this direction. So it has come back to the same point, which means A is correct, right? Right. Now we need to check the next statement. They're saying acceleration of the particle does not change directions during the motion. We will check. In a VT graph, what is given by the gradient? Gradient gives us, in a VT graph, gradient gives us what? The acceleration of the particle. Right? It gives us the acceleration of the particle. So if you check this gradient, right, it has a positive, opposite side is positive. The gradient is what? Also it is equal to tan theta. Tan theta means opposite over adjacent. Opposite is initially positive. This is also positive. T naught minus 0. It's positive. So the acceleration is positive initially for this instance, right? For the instance 1, when the particle is moving from A to B, it has a positive acceleration, right? So what about this? So here, if you check, it's going to have a negative displacement. Sorry, negative opposite side. Opposite side is, in the second case, the opposite side is negative. And then you need to take T naught minus 2 T naught, right? It's not 2 T naught minus T naught, because like you need to take the open side, like the mouth is open to this side. So this minus this. T naught minus 2 T naught gives you negative, which is negative over negative is positive. So when it is returning back also, it has a positive acceleration, even when it is moving forward and returning back. In both the cases, the accelerations are the same. It is simply an acceleration, not a deceleration. It's an acceleration, not a deceleration, right? So therefore, this is correct. It doesn't change, right? Therefore, that is also correct. Right. Let us check at t equal t naught. Right? They are saying at t equal t naught, the impulse acting on the particle is infinite. Impulse acting on the particle is infinite. At t equal t naught, what is impulse? Impulse means what? Impulse means the change in momentum, right? mv minus mu, that is impulse, right? F into t, impulse. So the initial momentum was mv naught, the particle of mass m, right? M, it attained a velocity v naught, right? And then thereafter at t naught, what happens? This is t equal to t naught, right? Initially it has a forward v naught, and then a second later it's having a velocity in the negative direction, negative v naught, right? So at this moment the momentum is, the linear momentum is m minus m v naught, right? M into minus v naught, because simply linear momentum means the mass into velocity, right? So at t naught, just before it turned its direction, it had a positive linear momentum. Just after it turned its direction, it has a negative linear momentum. So initial linear momentum is mv naught minus final linear momentum is negative mv naught. Final linear momentum is negative mv naught. Initial linear momentum is what? We need to consider the linear momentum in a certain direction, right? I will consider it in, maybe I'll apply impulse in this direction, the equation in this direction, right? So yeah, what is mv naught? What is final linear momentum? Final linear momentum is negative. Why? Because it's in the opposite direction. It's directed towards this side, towards the left. So therefore it's negative mv naught. Minus initial linear momentum is what? Initial linear momentum is mv naught. It's positive, it's directed towards the right. So therefore if you see 2m v naught, right? So it doesn't matter. The impulse in this direction is minus 2m v naught. Therefore the impulse in this direction is 2m v naught. This is a finite value, isn't it? This is a finite value. This is not an infinite value. It is a finite value. Therefore this is wrong. Therefore the only answers that are correct are A and B, right? A and B. Okay guys, let's discuss the 1996 problem. In the 1996 problem, of course, what they are saying is when two objects A and B collides with each other, in which of the following action and reaction forces are marked on the objects properly. Okay, so before we analyze the answers, let us straight away get the answers, because this is quite easy, you know, right? So let us assume the two objects are collided, right? Let's assume the two objects are collided. If this is A and if this is B, right? So you know this, when these two are collided, we usually draw without a contact surface, right? We draw it contactless, because that is how free body diagrams are drawn, right? You do not draw it such that it is contacted. That is because in that case you will not be able to clearly show the forces on which surface which force is acting. So therefore, like, we draw it contactless. Okay, fine. Now actually let's assume B is colliding with A. Therefore the force by B acting on A is this. Let's assume Fa, the action force. So according to Newton's third law, every action has an equal and opposite reaction. Therefore the force acting on B due to A is considered as the reaction force Fr, right? So what is this force? Actually it's the third answer, right? This is wrong. Why? Because the action reaction cannot be on the same object. Action reaction on the same object. Action reaction on the same object. So according to Newton's third law, the action reaction should be equal in magnitude but opposite in direction. Both are in equal direction. So this is also wrong. So therefore the correct answer is this, right? So guys, this is once again a question from 1996. That is like this is also simply a force and momentum change problem, right? They have given FT graph and then they have asked some question. Let's see what it is. A force capital F varying with time as indicated in the figure is applied to a wagon of mass 10,000 kilograms, which is initially at rest. This is very important, right? So the wagon is initially at rest. To that wagon, they have applied a force which varies as in this graph on a frictionless horizontal rail. After 100 seconds, we need to find the speed. To find the speed of the wagon, right? Okay, it's like this. For example, if we consider this as the wagon, right? A force capital F is applied on this wagon. Initially, the wagon was at rest, right? So this is, let's assume t equals 0 time. So from t equals 0 to t equal 50, let's assume at t equal 50, we need to find the velocity. Let's assume we need to find the velocity at t equal 50 seconds. The velocity at t equal 50 seconds. How do we find it? So simply, guys, to the wagon, we are going to apply what? F is equal to mv minus mu over t. So F into t is equal to mv minus mu. So what is ft here? In the first 50 seconds, how to find ft? F into t, this area, right? F into t, right? 1000 into 50. 1000 into 50. Force is 1000 into 50. The area, right? Area. What is the mass? 10,000. What is the final velocity? We do not know. 10,000. What is the initial velocity? It was at rest. It was at rest. So this complete terms goes to 0. So 1000 into 50 is equal to 10,000 V. So this 3 to 3, 4 cancels. V is equal to 5 meters per second. We have found the velocity at this moment is what exactly? Now it is 5 meters per second. It's found, right? Now we need to find next the velocity at the 10th second, sorry, 100th second. When t equal 100, we need to find the velocity v dash. What is this? It seems, right? So for this, from t equal 50 to t equal 10, the momentum change. I'm going to apply F equals mv minus mu. Okay, this is, let's assume a, b. So this I applied from a to b, right? Right? I applied from a to b. This I applied from b to c. All right. So ft product is equal to mv minus mu. What is the ft product? The ft product from t equal 50 to t equal 100 is minus 500 into, this is, what is the difference? What is the difference? 50. 50 to 100 is 50 minus 500. So it is minus 500 into 50. The mass is 10,000. I'll take the mass out. What is the final velocity? The final velocity is v dash. We do not know that. What's the initial velocity? At b, what is the velocity? 5. We know that. So here, of course, 3, 1. 3 cancels. 5 to this 2, right? Minus 5 over 2 is equal to v dash minus 5. So minus 5 taken to that side, it is plus 5 minus 5 over 2 v dash, which means v dash is going to be 2.5 meters per second, right? 2.5 meters per second. So actually the answer should be this, 2.5 meters per second, right? Okay, so that is the answer, guys. Okay, guys, so here, of course, this is a 1998 question, right? This is also once again a easier question, but can't help, right? So that is, those are the questions what is given from the Newton's laws of motion and force and momentum change section. So we'll have to, even though it's like you can see, right? So the same question is repeated. So therefore, like, past paper analyzation is very, very important, right? So that's what you need to understand. So here they are saying a body of mass 5 kilogram is subjected to a force capital F, which varies with time, the momentum gained. Momentum gained means what? The change in momentum, right? So for the object due to an application of force, this is how the force varies. So we will have to apply mv minus mu over t, right? So F into T is mv, or else the delta mv, the momentum gain, right? Force F into T. F is what? F into T is the area of this curve. F into T is the area under this curve. How do we find this area? It's a trapezium actually. It's a trapezium. Half into, what's the base? Half into perpendicular height is 10, right? The adjacent sides, if we add 6 plus 8, 6 plus 8 is equal to delta mv, the momentum gained, right? So this is going to be 5 into 14, right? 14. So delta mv is going to be equal to 4 times 5 is 0, 2 remaining, 70 newtons second, right? So this is going to be the answer. So it's quite easy, right? So yeah. Okay, so next guys, this is the 1998 problem as well, once again, right? So here they are saying two forces F1, which is 10 newtons, and F2 9 newtons are applied simultaneously to a stationary object at t equals 0, I guess, right? T equals 0 as shown in the figure. The force F2 is then, like, at time t equals 0 to t equal t1, I guess, right? Okay, that's a small printing mistake, right? Applied simultaneously to a stationary object at t equals t1, yes, and at t equals 0, at t equals t0, t equals t0, right? Okay, so let's mention that as t equals 0, right? T equals 0 as shown in the figure. The force F2 is then increased suddenly to t equal 10 at t equal t1, right? So initially at t equals 0, at t equals 0, right? So 10 and 9, which means that's going to be F equals 1 Newton in the right direction, which means there is a resultant force. If there is a resultant force, there should be an acceleration according to Newton's second law, isn't it? So if there is a resultant force, there is an acceleration according to Newton's second law. So therefore, how do we represent accelerations in a VT graph? By using a constant gradient. The gradient should be constant. So from t equals 0 to t equal t1. So in this, all these graphs, that's there. It's there, right? So okay, fine. Now next, what do they say? Now what they're saying is, at t equal t1, F2 is then suddenly increased to, F2 is increased to 10. This is increased to 10 newtons. Now F1, F2 both are 10 newtons, right? So both F1 and F2 are 10 newtons, which means there is no resultant. No resultant force means the acceleration should be 0. No resultant force means acceleration is 0, which means if the acceleration is 0, what does that mean? It's a uniform velocity motion. It's a uniform velocity motion. How do we represent uniform velocity motion? Uniform velocity motion. This is not true. This is wrong. This is fine. This is fine. This is fine, right? Okay. So we have eliminated the second answer. Right, now what? Then they are saying, and the force F1, is completely removed at t equal t 2t. At t equals 2t, the force F1 is completely removed, which means now only F2 force is there. So the object was initially moving in this direction with uniform velocity, right? Uniform velocity. Now if you apply a force in the opposite direction to the motion, this will go with a deceleration, right? It's going to go forward with a deceleration. It's not going to suddenly, like, like due to application of F2 in the opposite direction, it's not going to suddenly change its direction. So the uniform velocity should come to 0. I mean, like, it should decelerate first. It should first of all decelerate and come to 0, and then thereafter only it can change its direction. So this is possible. Decelerations. This is possible. This is incorrect. This is incorrect. Right. So out of these two, what is the graph? Now here, if you see, right, if you see this, the gradients, this gradient is higher, this deceleration is higher, this deceleration is lesser. Gradient denotes the deceleration, right? This gradient is somewhat higher. So this gradient is somewhat higher. It's a higher deceleration, right? This is a lesser deceleration. So guys, you know, like, you completely remove F1, only F2 is there, which means that this is a large force, right? This is a large force. Like, initially 1 Newton. For 1 Newton, this amount of a gradient, this amount of an acceleration. For 10 Newtons in the opposite direction, it should be a very large deceleration. The gradient should be somewhat large. So therefore, the answer is this, not this. The answer is the third one, guys, right? So let us discuss the rest of the problems. I mean, the 1999 from 2000 onwards in the past paper discussion of Newton's laws of motion, session 2, right? So this is the session 1. Make sure to cover the session 2 as well, right? So likewise, this is going to be a series, right? This is going to be a series of the past paper discussions, right? So thank you, guys.